Today, I would like to talk about one of the applications of Monte Carlo simulation, which is the search and rescue optimal planning system. Here's the outline. First, we talk about the background of the system, and then we talk about its components, the sim part, and the planner, and how can we actually simulate this, and the expected results, and also how can we further improve this. The background is very simple since it's very difficult to search a person on a giant sea. So we need to find a systematic way to do it, and also we need to optimize the rescue assets, and so as to maximize the maximum probability for saving a life. And the major components, as mentioned, are the environmental data surface, and the simulator, the sim, and also the planner. So in the sim, first we have to understand the concept of probability of containment, which describes the factors affecting a target's location, like the water currents and also the wind speed. And based on these factors, then we will generate a Monte Carlo set of paths for these scenarios, what might have happened to the targets, and also use heuristics and experience to aid this simulation program. So the environmental effects on drift are mainly twofold. We have the current and the wind, and we have different forces acting on the particles, and realistically these data are obtained from the environmental data surface. So how can we actually do this if we don't have the data to simulate the particle tracks? We use the Lagrange particle tracking algorithms. The B term is the diffusion coefficient, and the C is an independent random number, so we introduce randomness to the particle's position and see how the planner will actually capture this particle or the targets. And A is the function that describes wind and the current conditions, which can be time dependent and also position dependent. And based on these particles, we will define the area into grids, and then we count the number of particles that fall into each grid, and then we have our probability of containment. Here is an example of the algorithm we talk about. However, this example is a bad example, as you can guess, because when X and Y are getting further and further away from the origin, actually there are no maximum limit on how this gradient actually can be, so it is not realistic, and this is a bad example. And there are mainly four ways to perform a search on an area, which is the parallel track search, and also the creeping line search, and the sector search, and the expanding square search. From the resources that are found in the paper and the information provided by the practitioners, and also the current methods that the coast rescue team is using, they're using the parallel track search because they think that is the most efficient over water and flat terrains, which is the case on the sea. And on the right hand side of this slide, we can see the lateral range curve, which describes how the probability is affected when the target and the detecting units distance vary. For example, if the distance between the detection facility, the detection units like a plane, and the target is very large, so it's like -8 and 8, actually it will not be seen, so the probability is very small. And the next thing we have to talk about is how the weather will affect this probability of being detected. So from the information provided by the paper, it mentioned if the wind speed of the wave height is too high, then the probability of the search and rescue targets will actually decrease a lot, and this is a correction factor that we need to include in our simulation too. So from these constraints hinted by the papers, we will know that what the lateral range curve will be like but that is in 1D, so we need to construct a function in 2D as well, and also the correction factor due to the adverse weather conditions, and also a penalizing function that we'll talk more about later why this is true. And given that probability of detection is a probability, so we need to normalize it to 1 as well. So this detection probability in 2D is symmetric in the theta direction and is slowly decreasing along the R direction. And from this information and from this proposed 2D lateral range function, we will know the probability of detection. So basically the concept of probability detection is describing how likely, how advantageous if the plane is at that cell to detect a target. And here is why we need the penalizing function, because when the search area is too large, then it has a high possibility that the plane will need to fly faster and it will miss the target, so a lower success rate is obtained. And this is a trade-off, and we need to include this in the simulation to make it more realistic. So from the set of Monte Carlo points that we generated using Lagrange particle tracking algorithm, how can we generate a rectangle from these Monte Carlo points? And from this Graham algorithm, we can see, given these points, we need to generate a convex hull. So what is a convex hull? Is to make sure every turn on the outer part of this line is actually turning left instead of turning right. So here we will see is counterclockwise and clockwise rotation. And if that point is counterclockwise, then we need to backtrack until this point actually becomes a counterclockwise rotation. And in the end, we will expect to find a convex hull from this algorithm. Next, we will talk about, after we generate this convex hull, which is something like this, and the points all rest inside this convex hull, how can we generate a minimum area rectangle? Because the generation of minimum area rectangle is very important. We will need to have a parallel track search sequence that we can obtain for the planner to optimize. So this rotating calipers algorithm is testing the rectangles generated from these edges and then select the one that is the smallest, like this diagram shown here. So what is the heuristic algorithm behind this planner? It will try to select a parallel track search from the rectangle we generated, and it will select the highest probability of success that a certain tracks can provide. And once that maximum is arrived, then we will no longer need to improve the map further. So how can we perform the Bayesian updates from unsuccessful search? Even, let's say we are very unlucky and we haven't got the targets even after all that is done. Then we will look twice and we will we will try to do as the screen here on the slide sets, and we look along the path and try to perform the Bayesian updates for these maps. Here is the simulation steps recap. First, we generate a set of particles from Lagrange particle tracking. Then we generate a convex hull from the Graham scan, and then the rotating calipers. And we'll calculate the probability of containment, and we'll calculate the probability of success for each parallel track search. And after we find the track search, we will execute the plan to see if we find a target. If we don't find it, then we'll update it, and then we'll repeat these steps until we can find it, or until a maximum search of n times are done. So here are the expected results. As you can see, there is a convex hull and there is the optimal parallel track search. And these results are actually provided by the paper. So we will try to do our own, see if we can find one. Here is the further improvements that we can do to this experiment. And in the code report, we will do some demos to show how this algorithm can successfully incorporate the information from Bayesian updates, and also when this algorithm fails within, say, like 3 maximum searches, and calculate the success rate of this illustration of planning system. So that's it. Thank you.